Okay, welcome back. Today I'm going to discuss two examples about path integral. The first example is a simple uh, scalar balloored integration. It states xyz ds and the path is given. The second example is an application of the path integral where you want to calculate the average temperature of air in the shape of an helix, and helix is given. So this is again an integral, but now the temperature field has to be given here. So let's just write down the temperature field uh, here. X square plus y square plus z square is the temperature field. Okay, so I have solved and demonstrated of similar examples earlier. I am repeating it just to help some students, and I have some requests from some students to provide some examples. Okay, so let's get started with the first example. So for this type of simple integration, uh, which is called the path integral, the first thing you look at the path and the parameterization and the limit. So here the limit is for t from 0 to pi by 4. So the integration will be going from 0 to pi by 4. The parameterization tells us what is x, what is y, what is z in terms of the parameter t, and the integrand is x, y, z. So let's write down that. Okay, so ds, which is the arc length, is the magnitude of the derivative of r or r prime t. So let's write down here r prime t, which is the derivative of r. So r is here. So if you differentiate, sine of 2t will be 2 cos 2t, right? So cos of 2t, so negative 2 square root of 2 sine 2t, and then 2 cos 2t with respect to t. Now we can see the integration is not a complicated one. We can simplify. You can see here sine of t, you can write it sine square 2t, sine of 2t, sine of 2t. So negative square root of 2 sine square 2t cos 2t. Okay, so now in this part here, we have to take the magnitude of this vector. So to take the magnitude, I will write the square root, and then magnitude is square each component and add them together. So 4 cos square 2t plus 8, 2 square root of 2 square is 8, sine square 2t, and then the third term 4 cos square 2t dt. Okay, so let's simplify the quantity inside the square root first. So just put whatever as is. here. Okay, so we can see here 4 cos square 2t, 4 cos square 2t, which will be 8 sin square 2t, sorry, 8 cos square 2t, and this one is 8 sin square 2t. So 8 is common, it comes outside the square root, becomes square root of 8 to square root of 2, and inside the square root you have now cos square 2t plus sin square 2t, so that is 1. So you don't have to do anything. Then finally the integral is, you can see here square root of 2 to square root of 2, you multiply that, you get negative 4 pi by 4, not pi by 2. And here we can just simply do a u substitution of what we will be substituting. Well, so sin 2t cos 2t, anyone works. The easy would be if I substitute sin 2t for u, then I get du is 2 cos 2t. So 2 cos 2t, I can write here cos 2t dt is a dt, cos 2t dt as half du, and I will just forget the limit. We'll solve it as independent integral. So sin square u, which is u square, cos 2t dt is half du, okay. So the integration will be now, you can simplify 4 divided by 2, which is 2, and then u square antiderivative is 1/3 u cube, and u is sine up to t, which is cube, and 0 to pi by 4, negative 2 over 3, and sine cube 2t, because t is pi by 4, so 2t is pi by 2. Sine pi by 2 is 1, sine cube pi by 2, pi by 2 is 1, and then minus 0, which is 0. So this is the answer. The answer is excuse me, answer is negative. Answer is negative because due to the direction of the path. So for this example, we are going to discuss why it is negative or positive. As we mentioned earlier, that the path integral can be negative. The point that I want to mention is we can repeat this exercise. So repeat means, I want to say, is solve xyz ds. Solve xyz ds with a new parameterization. With a new parameterization, which is minus cos of t by square root of 2 square root of 2 sine t by square root of 2 cos t by square root of 2. Okay, and t going from 0 to this time pi by 2 square root of 2. Okay, and I leave this as an exercise. You can show that the answer will be minus 2 over 3, the same answer. So what I want to say is that perhaps you can find another parameterization of the path C, and then the integration will be the same -2/3. It is because a curve can be parameterized in many ways. Every person may come up with their own parameterization. Finally, the result should be the same. So we can state this as a theorem. So suppose that let RT be a parameterization of path C. A parameterization of path C and f is a continuous function I would say on the image of C. If you look at f on C, it is a continuous. F can be discontinuous outside C. Now suppose gamma t be a second parameterization of C. Then, so the path integral, I will write here R of t to mean that the parameterization of the path is R of t. So path integral on R of t of f ds is the same as path integral of gamma t f ds. We don't have to learn how to prove that. That's the main message that we have to keep in mind, is that the parameterization is not unique. Regardless of this, the integration will be unique. The final answer will be the same, as long as the function is continuous on the path. Well, if the function is discontinuous, we might not be able to solve the integral. We have to solve the integral partially, so that is something we will not be discussing here. The second example, that's just for clarity, copy it here. Okay, so you want to calculate the average temperature, right? So here we are asked to find the average temperature on the helix. So the temperature will be the integral of the temperature on the helix. So that is the total temperature. If you divide this by the length of the curve, that will be the average temperature. Let's put a bar, T bar, that's dash on the top of T, which is a symbol for average, commonly used in science and technology. T bar, 1 by L, L is the length and the integral. So then you have two jobs. Find the integral, find the length. So which one first? It depends on you. So I'm going to first calculate the length. Okay, so length of the curve C, length of the curve C, length of the helix. Helix is given in terms of a parameter T, going from 0 to 10 pi. So how do we calculate length? So uh, my strategy is always that we do not want to memorize a formula for length. A formula for length can be stated, written in different ways. So there is no unique way of writing the formula. So when we go to memorize the formula of arc length, we are in troubles. So rather we try to understand the concept. So the strategy of finding a length is you integrate 1 on the curve. If you integrate 1 on the curve, and this is the way we did surface integral also. If we integrate unit vector on the surface, we get the surface area. So similarly, we integrate 1 on the curve. So integral 1 ds. Later on, we will show that this way we can calculate the volume. Okay. So parameterization is given limit 0 to 10 pi. We don't have to do anything with the 1. ds is r prime. So r is magnitude of r prime t. So you can just straightforwardly write r prime, its value. So r is cos t, tan t, sin t. Differentiate this. Okay, see, did I write it correctly? Yes, hopefully. So put here 0 to 10 pi. We are not done yet with the integration. We look at the magnitude, put square root sine square t plus 1 by 100 plus cos square t. So that's a constant, is because sine square t plus cos square t is 1. 1 plus 1 by 100 will be 101 divided by 100. So square root of 101 divided by 100, or divided by square root of 100, which is 10. And the integration from 0 to 10 pi dt, which is just t, from 0 to 10 pi. So if you substitute that, 10 cancels, square root of 101 pi, which is the length. Okay, so now we can calculate the total temperature, which is the integral T ds. So we know the limit going from 0 to 10 pi. T is x square plus y square plus z square. X is coming from the parameterization. X, y, z. X, y, z. This cannot be missed. So this is why we don't want to memorize the formula. So what is x? Is the first component of r. Because r is my parameterization. We are converting x, y, z to r of t. So the first component of r is my x. Second component of r is my y. Third component of r is my z. So x square will be here cos square t plus y square will be t square by 100 plus z square will be sin square t, and then r prime just to be clever, I will write r prime t, and because r prime t has already been calculated when I have calculated the length, so I don't need to repeat that calculation. I can carry out. So here cos square plus sin square, which is 1, which is 1, and plus t square divided by 100. R prime t, we showed here, this is R prime t, 1 plus 1 by 100. So this quantity, square root of 101 divided by 10 dt. Okay, so square root of 101 divided by 10 goes out. This is a very easy integration. T plus 1/3 t cube divided by 100. X square plus, okay, so I have a little typo here. Let me just to make the integration easy, go back and change the temperature. That's correct, but maybe the integration we will have to deal with this cube. So what I'm going to do is just, it is not necessary. I'm going to remove this square from here, just because we want to demonstrate the method, not complicated integral. So if I remove that square, what happens is just this term here will be changed. So let me just rewrite that. So that is t over 10. So that is t over 10, 1 plus t over 10, right? So t plus now will be t square over 20, and limit going from 0 to 10 pi, right? So 101 divided by 10, and you can figure out is really straightforward. 10 pi plus 100 pi square divided by 20 means 5 pi square. So keep 101 square root outside, and then take 1 by 10 inside. So it will be pi plus half pi square. Okay. Now average temperature T bar equal to 1 by length integral T ds. Here is it. Type again, it should be ds. Okay, T ds. So 1 by L, L is here, 1 by 101 square root pi, and integral T ds, which is square root 101 times pi plus half pi square. So 101 get cancelled. You can see pi can be taken out from here. Take pi out, will be 1 plus pi by 2. 1 plus pi by 2. When pi goes out, it gets cancelled. Pi goes out, it gets cancelled with this guy. Okay. So hopefully this is clear and should cover sufficiently how we can solve path integral of scalar valid scalar valued functions, integral f ds. We have covered two important points. One point is that the parameterization can be different. As long as correct, the integration will be the same regardless of the parameterization. Second point we try to understand is the average quantity, how we calculate on a path. So the average quantity will be the total divided by length of the path. So we need to calculate arc length. So another option or another objective of this exercise is to practice arc length, calculation of arc length. Okay, thank you very much.